Imagine looking up at the night sky on a clear, dark night far from city lights. You're seeing countless stars, each a sun, burning for billions of years, radiating light and heat across unimaginable distances. Each one a unique story of stellar evolution. But some stars, the true giants among them, possess a destiny far more dramatic. They end their lives not with a whimper, but in a spectacular explosion, a supernova, a cataclysmic event visible across light years. This is one of the most energetic events in the universe, a phenomenon that briefly dominates the cosmic landscape. It's a cosmic fireworks display of unimaginable power, a stellar explosion releasing more energy than our sun will emit in its entire lifetime. For a brief moment, a fleeting instant in cosmic time, a single supernova can outshine an entire galaxy of billions of stars, becoming the brightest object in its celestial neighborhood. But a supernova is more than just a bright explosion. It's not merely a destructive force, it's a transformative event, a pivotal moment in the ongoing saga of the universe. It marks the end of a star's life, the dramatic conclusion to a multi-million or billion-year story, and simultaneously, the beginning of something new, a catalyst for creation on a grand scale. The explosion scatters elements forged in the star's core, elements created through nuclear fusion. These elements are propelled far into space, carried on the shock waves of the explosion. This process is seeding the cosmos with the building blocks for planets and ultimately, life itself. These cosmic detonations are fundamental to our understanding of the universe, providing insights into stellar evolution and the creation of elements. They recycle and redistribute matter on a galactic scale, ensuring the continuous cycle of star formation. This process is enriching the cosmic soup for future generations of stars, providing the raw materials for new stellar nurseries. The elements in our bodies, the very atoms that make up our being, our planet, and everything around us, from the air we breathe to the ground we walk on, were once part of such explosions, forged in the heart of a dying star and scattered across the cosmos. So what exactly is a supernova? What defines this spectacular event? It's a star's grand finale, a beacon of energy, a cosmic factory, and a testament to the dynamic nature of the universe. Join me as we journey into the heart of these incredible phenomena to witness the death throes of stars and the birth of new possibilities. Let's discover what happens when stars go supernova and unravel the mysteries behind these awe-inspiring events. Not every star ends with a bang. Some fade away quietly, while others meet a more dramatic fate. Our sun, for example, a relatively modest star, will quietly shed its outer layers over billions of years. Eventually, it will cool and contract, becoming a white dwarf, a dense, fading ember in the vastness of space. But supernovas, those awe-inspiring stellar explosions, are reserved for the true heavyweights of the cosmos. These are stars at least 8 times, and often many times more, massive than our sun. They represent the upper echelon of stellar existence. These giants burn bright and live fast, consuming their vast reserves of fuel at an astonishing rate. Throughout their tumultuous lives, they are engaged in a constant, relentless battle between gravity pulling inward, trying to crush the star, and nuclear fusion pushing outward, a powerful force generated in the star's core. Fusion in the core releases tremendous amounts of energy, creating outward pressure that perfectly balances the inward pull of gravity, keeping the star stable and preventing its collapse. But this delicate equilibrium cannot last forever. When a massive star runs out of fuel, specifically the hydrogen and helium at its core, fusion falters, the energy production wanes, and the outward pressure begins to diminish. Inevitably, gravity takes over, unopposed and relentless. The core, now devoid of its energy source, contracts rapidly under its own immense weight, compressing matter to unimaginable densities and setting the stage for a dramatic end. Unlike smaller stars, which can sustain themselves for billions or even trillions of years, these giants burn through their fuel at an accelerated pace, living short, brilliant, and ultimately explosive lives. When their fuel is completely exhausted, gravity delivers its final, crushing blow, initiating a catastrophic sequence of events. The star's core collapses in a fraction of a second, triggering a chain reaction that leads to a supernova. The journey toward a supernova begins. Their grand scale dictates a rapid, violent demise, a spectacular display of cosmic power. Only the most massive stars, those titans of the stellar realm, get this explosive send-off, a fitting end to their extraordinary existence. The universe saves its most spectacular fireworks, its most dazzling displays of energy and light, for its biggest and most influential stars. The stage is set for a cosmic cataclysm, a supernova that will briefly outshine entire galaxies. As a massive star nears its end, its core becomes layered like an onion, with heavier elements at the center. Fusion creates shells of silicon, oxygen, neon, carbon, helium, and hydrogen. Each layer fuses lighter elements into heavier ones, but there's a limit: iron. Fusing iron doesn't release energy. It consumes it. When the core is mostly iron, fusion stops and gravity wins. The iron core grows as more silicon fuses, reaching a critical mass, the Chandrasekhar limit. At this point, the core can no longer resist gravity. The core, with more mass than the Sun but only the size of Earth, becomes catastrophically unstable. It collapses in on itself, triggering the final act. The star has run out of options. The collapse is inevitable. This is the tipping point, the moment before detonation. The final rapid collapse is about to begin. The stage is set for one of the universe's most violent events. When the iron core collapses, it shrinks from the size of Earth to a city in less than a second. The core's density skyrockets, crushing protons and electrons into neutrons and releasing a flood of neutrinos. The core becomes a super-dense neutron star, resisting further collapse. In falling material slams into this hard core, creating a powerful shockwave. This shockwave blasts outward, tearing through the star's outer layers. The explosion heats the star to billions of degrees, triggering a final burst of nuclear fusion. The energy released is colossal, enough to outshine an entire galaxy for weeks. The star is ripped apart, flinging enriched gas into space at thousands of kilometers per second. For a brief time, a supernova becomes a beacon visible across the cosmos. We see it as a new star suddenly appearing in the sky. The star dies, but its death illuminates the universe. This is the visible spectacle of a supernova, a cosmic event of almost unimaginable power. The universe is forever changed by this explosion. After the cataclysmic explosion of a supernova, the universe is left with a profound question. What exactly remains at the heart of this stellar upheaval? What becomes of the star's core after such a violent event? The answer depends critically on the original star's mass. The more massive the star, the more dramatic its final transformation. If the star was massive, a giant in its own right, but not quite extreme enough to reach the highest mass echelons, the core undergoes an incredible compression, ultimately becoming a neutron star. This is an object with more mass than our entire sun, a colossal amount of matter all packed into a sphere just 20 kilometers across. Imagine squeezing the sun into a city. The density is so extreme that a teaspoon of neutron star material would weigh billions of tons here on Earth. It's a mind-boggling concept to grasp. Adding to their mystique, some neutron stars spin rapidly on their axis and emit powerful beams of radiation from their magnetic poles, sweeping across the cosmos like a beacon. These are pulsars, the universe's lighthouses, sending out regular pulses of energy that astronomers can detect across vast distances. But if the original star was even more massive, a true behemoth among stars, then gravity wins completely, crushing everything in its path. The core collapses beyond the point of even a neutron star's existence, ultimately forming a black hole. This creates a region where gravity is so overwhelmingly strong, an inescapable abyss, that not even light, the fastest thing in the universe, can escape its grasp. Because light cannot escape, black holes are inherently invisible to direct observation. However, we can detect them indirectly by observing their profound effects on nearby stars and surrounding clouds of gas, which are distorted and pulled in by the black hole's immense gravity. Both neutron stars and black holes, in their own unique ways, are fascinating and enigmatic relics, the silent tombstones marking the death of a star. They are scattered throughout our vast galaxy, the Milky Way, silent witnesses to the cataclysmic events of ancient supernova explosions, long since faded from view. These remnants stand as a testament to the universe's capacity for extremes, representing some of the most extreme objects in the universe. The aftermath of a supernova, therefore, is not merely an ending, but a dramatic transformation, as profound and awe-inspiring as the explosion itself. From the incredibly dense neutron stars to the all-consuming black holes, these exotic objects play a crucial role in shaping the structure and evolution of the cosmos. They are the enduring legacy of a star's final, spectacular act, a reminder of the dynamic and ever-changing nature of the universe. Supernovas are not just destructive, they're creative. During a star's life, it fuses elements up to iron, but heavier elements like gold and uranium are made only in the chaos of a supernova. The explosion floods atomic nuclei with neutrons, creating new, heavier elements in seconds. These elements are blasted into space, enriching the galaxy. Without supernovas, the universe would be mostly hydrogen and helium. No rocky planets, no complex chemistry, no life. Every atom of gold, calcium, and iron in our bodies was forged in a supernova. The explosion seeds the galaxy with the ingredients for new stars and planets. Supernovas are the universe's master alchemists. They transform the cosmos, one explosion at a time. The story of matter is the story of supernovas. We owe our existence to these cosmic forges. Humanity has witnessed supernovas for millennia, long before we understood their true nature. In 1054 AD, a supernova in Taurus was so bright it was visible in daylight for weeks. Its remnant is the Crab Nebula, still studied today. Tycho's supernova in 1572 shocked astronomers, challenging the idea that the heavens were unchanging and fueling the scientific revolution. In 1987, supernova 1987A in the Large Magellanic Cloud became the first to be studied with modern instruments, confirming our theories about core collapse. These events have shaped our understanding of the universe. Each supernova tells a story of stellar death, cosmic change, and scientific discovery. They connect us to the cosmos and to the history of human curiosity. Supernovas are not just distant explosions. They are milestones in our quest to understand the universe. Supernovas don't just create elements, they shape galaxies. Their shockwaves compress clouds of gas and dust, triggering the birth of new stars and planetary systems. The death of one star can lead to the birth of hundreds more, a cycle of cosmic death and rebirth. Supernovas stir up the galactic disk, influence star formation, and enrich the interstellar medium. They also accelerate cosmic rays, high-energy particles that pervade the galaxy and even reach Earth. These explosions help determine a galaxy's structure and evolution. Supernovas are dynamic architects, constantly reshaping the cosmos. Their influence extends far beyond a single explosion. Why do supernovas matter to us? Because they are the reason we exist. The elements essential for life, carbon, oxygen, iron, were forged in stars and scattered by supernovas. Our solar system formed from clouds enriched by ancient stellar explosions. The atoms in our bodies, the Earth, and everything around us were once part of long-dead stars. We are, quite literally, made of stardust, supernova dust. This connection links us to the grand cycles of birth and death in the cosmos. When we look at the night sky, we see our own origins. Supernovas remind us that destruction paves the way for creation. They are a testament to the interconnectedness of everything in the universe. We are children of the stars, born from their fiery death,